Okay, in the last video we introduced the idea of geometric isomers, one form of stereoisomers. You need to have a double bond, and the double bond, of course, has got a pi bond. It's got a pi bond there, and that means it can't rotate without breaking the bond. So that means you could have the chlorines in two opposite, 1,2-dichloroethene we've got here. We've got the two chlorines on the same side of the molecule. We call that the Z form. And here we've got the two chlorines on the opposite side of the molecule. We call that the E form. And they're going to be two different molecules. Right, let's have a look at some more examples of it. Okay, so let's have a think about ethene. Okay, now ethene is like that. Okay, and don't forget that's a flat structure. You can't have two different forms of ethene. There aren't two geometric isomers, because all you've got attached around the carbons is you've got 4 hydrogens, and so there's a symmetry there, and there aren't two versions of it. However, let's say if we replace, let's have a think about this molecule. Okay, you would call that but2ene, wouldn't you? Okay, but2ene. Now, first of all, before we think can that exist as geometric isomers, I'm going to take issue with the way that I've drawn that, which is why a lot of people who draw it. I've drawn that. I haven't really shown the bond angles there. It looks like you've got 180 here and you've got 90 there. Yeah, but it's not like that. Every bond angle around those carbons with the double bond is 120. So let's draw it how it is first of all. Now let's think, what have we got attached to this carbon? Well, we've got a hydrogen, which I'll draw there, and the other thing we've got attached to it is a methyl group. So I'm going to draw that like that. Same with the other one, we've got a hydrogen attached, and we have got a methyl. Now, can that exist as two geometric isomers? Right, hopefully you can see that it can, because I could draw another version of that. Right here, I'm going to draw, the methyl there is the same, but I'm going to put that methyl on the other side. Don't forget, this is a flat structure, really. All the bond angles around every carbon is 120. So you can see, and this one, we have got the two methyl groups are on the same side. So this is the Z-but2ene together, the zuzamen, and this one is E-but2ene, and they are different isomers of each other. Okay, so I'll have a look at a few more examples, but I think it's quite important what I recommend you do is when you go from this sort of like linear way of representing the molecule, and you redraw it to show the trigonal planar carbons. Okay. Okay, so let's have a look at but1ene now. Okay, we can go down here. Right, let's have a look at but1ene. You probably draw it out like this. Not making any effort to show what the real bond angles are. Right, so this hydrogen's here. Yeah. Right, now let's draw that with the proper geometry around the double bond. So putting my double bond here, what have I got attached? Right, to this carbon I've got a hydrogen and a hydrogen, so H and an H. What have I got attached to this carbon? I've got an H and I've got an ethyl group. Now, can that exist as two stereoisomers? Well, let's have a think. Let's draw. Let's swap that around. Put the hydrogen there and put the ethyl up here this time. Well, hopefully you can see that these two things are exactly the same as each other, aren't they? The green one is just like the red one that's been flipped over. So there's no difference between those two molecules. So no EZ isomerism there. No geometric isomerism, no EZ forms. And it's because of these two hydrogens here. When you've got the same two things attached to one of the carbons, it doesn't matter if you flip these around, swap places, because it's, you know, they're the same. So that's why there's no possibility of geometric isomers in that molecule. Right, let's just have another one here. So I'm going to adapt that molecule. I'm going to change it so that what we said that, right? This, because you've got two hydrogens attached to this carbon, you can't have the possibility of geometric isomerism. What happens if I what happens if I make one of them something different? If I make it a let's think, if I make it a methyl group, okay? Now you probably draw that molecule. You probably wouldn't draw it like that, would you? You'd probably draw it like this. Draw 5 carbons in a line, and you put a double bond in there, and then you put your hydrogens on. Or you might draw it in the, you might draw it CH3, CH2, CH, CH, CH3. And if you did have it drawn in these black forms, I would strongly recommend that you convert it into the blue form before you decide whether it can show geometric isomerism. Well, that can show geometric isomerism, can't it? Because look, you have got the methyl group and the ethyl group are on opposite sides of the molecule. So we would call that the E form of it. And what is it? It's 1, 2, 3, 4, 5. So it's E pent 2 ene is that molecule. That's what that is. And it can show. You could probably draw the Z form. Just swap you could swap these two about, couldn't you? The carbon and the methyl. Okay, just a little bit of a word of warning here about naming these. What I'm going to do is I'm going to subtly change this. So I'm going to rub the name out. All right, and I'm going to change this hydrogen for a methyl group. Should really have that bond joining up to the carbon there. Right, so what is that? It is actually, what is it? So it's 5 carbons long, isn't it? So it's pent 2 ene, but it's got so it's 3 methyl pent 2 ene. That's what we've got there. 3 methyl pent 2 ene. Okay, let's rub that out. So there, hopefully you can see that that does exist as 2 geometric isomers. I'll draw it in green, the other version of it. Oops. Come back. Right. So let's draw this. So I've got C. I don't know why it does that. I'm touching something on the keyboard. It's very annoying. Okay. Right. Almost as annoying as yesterday when the bin men came halfway through one of my videos and made loads of noise and I had to scrap it. Or when the dog starts barking. Right. Okay, so I'm going to put CH3 there, here, and then the hydrogen there. And I'm going to put CH2 there and CH3 there. Put the ethyl on the top this time, and this one here. Now, so this is 3-methyl pentuene as well. So now you may think, right, which one's the Z and which one's the E? You may think, all right, let's have a look. We've got 2 methyls there, and the methyls are on opposite sides, so that's going to be the E form. That you'd actually be wrong there, okay? Because strictly speaking, what you do is you have to, with these groups, you have to assign priority. So let's put this here. You assign priority. And there are some complicated rules, so that basically the bigger the molecular weight, the bigger the mass, the higher the priority. So let's asterisk the priority groups on each carbon. So let's look at this carbon here, right? And assign the priority. Well, we've got a methyl group and an ethyl group attached, and obviously the heaviest bit is the ethyl. So that's the high priority group there. Draw a circle around that. Let's have a look on this carbon here. Well, the highest priority group there is the methyl, isn't it? Because that's got the biggest weight, the biggest mass. Okay. So here with the 2 high priority groups are, so the priority, so the high priority groups on opposite sides, then we call it the E, the Entgegen form, and conversely, when the high priority are on the same side, then we call it the Z form. So which form is this one here? We can see here, right, the 2 high priority groups are opposite, so that is the E form. Whereas here, the 2 high priority groups would be the ethyl and the methyl. They're on the same, so that's the Z form. So you do have to be a little bit careful sometimes with that. Before we finish, give a couple more examples on that. So should we just get rid of all of that? So here's one a bit more obvious. So if I've got this substance, which is sorry, it's too big. I'll get rid of it. Right. So let's have a chlorine there, a hydrogen there, a fluorine there, and let's have a bromine there. Okay, so you would call that 1 chloro, 2 bromo, 3 fluoroethene, alphabetical order with those halogens. So let's see the highest priority with chlorine and hydrogen. Okay, so chlorine is obviously the heaviest one there, and bromine is heavier than fluorine. Is further down group further down group 7. So the one I've drawn there, that the 2 high priority groups are opposite, so that would be the E form. Okay, and so the Z form would be that way around. With the 2 high priority groups on the same side, the chlorine in that case, and the bromine would be the higher priority there. Okay, just another one more before we finish up. Let's put a double bond there, and let's have a hydrogen there, and let's have a methyl there. Let's put an ethyl there, CH2, CH3, and let's have a propyl group. So that's CH2, CH2, CH3. 3 there. And I've drawn normally you'd probably draw that as well. How many carbons long is it? 1, 2, 3, 4, 5, 6, 7. So you'd normally draw it like that. 1, 2, 3, 4, 5, 6, 7. And the double bond is 1, 2, 3, between 3 and 4. I've only drawn 6 there, haven't I? Double bond is between 3 and 4, so it's there. And put the hydrogens on. You'd probably normally draw it like that, but that wouldn't show you the geometry around the double bond. It's important to show that that is, it is geometry, yeah. There's all your hydrogens. The geometry really is 120 bond angles there, isn't it? Now, let's just do the high priority groups here. Well, we've got on this carbon, we've got methyl and propyl. So propyl is going to be the highest priority group. And hydrogen and ethyl, that's the highest priority group. So that version there I've drawn is the Z form. Okay, right. Just to show you how these are drawn in skeletal formulae, let's just do that very quickly. I'll do it with butene, okay? Okay, butene. Right, I'll draw here. Here I've drawn that's the Z form, isn't it? Your two high priority groups together, two methyls together. And here I will draw the E form. So all I've got to do is swap one of those. I've left that one the same. We're going to swap this side round, the H and the CH3. Now, if you're going to draw the skeletal formulae, you draw it like this: 1, 2, 4. Okay, and here's the double bond. Now you can see here. Well, I'll just draw it again. I'm going to draw circles around it. You've got a methyl group there, a methyl group there. What have you got here? You've got an invisible hydrogen, and here you've got the invisible hydrogen. Right, the two methyl groups are opposite each other, so that's how you draw the E form. Now, if you wanted to draw the Z form, and again, at A level, they've never asked you to do this, but it's not difficult to understand, and it is the way things are drawn. So if I draw, right, you draw the Z form that way around. There's the double bond. So if I draw that again, and put on the invisible hydrogens and stuff, yeah. So we've got a methyl group there, and here's our invisible hydrogen, which is kind of, they're on the same side. So in skeletal formulae, you are showing these as generally around here. They do have a 120 bond angle, and they've got a 120 angle in the diagram. So that's how you would draw the Z form. Okay, so if I draw another one, right? Right, that's 1, 2, 3, 4, 5, 6. That's hex-2ene, and that is that's the Z form, isn't it? And if I drew its the other isomer of it, I would draw it like that. That is the E form. Okay, I think I've gone on a bit too long there, so I'm going to stop now.